test it for the entire period?
Well, I did record the other class already, so I got that with these. All right, everybody. So we are currently recording, and I think it's doing the right thing. So let's go here. Let's go here. All right. So yesterday we introduced covalent bonding. To start class today, I would like you to take 30 seconds and talk to the person next to you. And I want you to compare and contrast ionic bonding, and covalent bonding. Compare and contrast ionic bonding, covalent bonding. 30 seconds. 15 seconds.
Between the nuclei of other
5 seconds. All right. So let's start with the similarities. How are ionic bonding and covalent bonding similar to one another? That was good.
The bond between two atoms.
The bond between two atoms. What is a bond? How have we described a bond?
An attractive force that holds atoms together.
Okay, so they're both attractive forces holding atoms together. What else? How are they similar to one another? Rachel, go ahead.
Both the bond acts in a way so that each atom has 8
8 valence electrons in both cases, all right? What else makes them similar? There's one more thing I would throw into the makes them similar category. 8 valence electrons is important because why? Lowest energy state, right? That's an important idea. Regardless of how we get there, lowest energy state is important. Okay? All right, contrast. How are ionic bonding and covalent bonding different from one another? Jules, go ahead.
Ionic bonding is between a metal and a non-metal, and then covalent is between two non-metals.
So ionic bonding is between a metal and a non-metal. Covalent bonding is between two non-metals. That's good. Yes, that's right. Okay. Let's talk. There's one other thing that makes them different. Why is that the case? Delvin, go ahead.
In covalent bonding, don't the nuclei, they can form a bond as well within an electron?
Well, we said that the attraction there is between the nucleus of the one atom and electrons in the other atom. And that's kind of what holds them together. Why? Let's talk more about electrons as far as the difference goes, okay? From an electron standpoint, how are ionic bonding and covalent bonding different?
Covalent, you like share.
Good.
And then in ionic here, it's like switching. I don't know.
Good. Right?
Yeah.
So, and that was on recording too. Just
Wow.
all right. So
It's right there record, so there's no.
hopefully the sound. All right. So Roman numeral number 1. On your outline from yesterday, Roman numeral number 1, letter D and E, we left blank yesterday. That's our comparison between ionic bonding and covalent bonding, right? In ionic bonding, electrons are transferred between atoms. And Jules said ionic bonding takes place between what two types of atoms?
Metals and non-metals.
Metals and nonmetals, because metals are looking to lose their electrons and nonmetals are looking to gain electrons.
Oh.
But covalent bonding takes place between two nonmetals because they're sharing those electrons, right? In order to share something with somebody, you both have to want that same thing, right? And that's why we have covalent bonding between nonmetals. Okay? Good there? All right. Yesterday, while covalent bonding involves sharing of electrons, we defined what a covalent bond is. So what is a covalent bond? Ryan, go ahead.
An attractive force that holds atoms together.
That's a bond in general. What's a covalent bond specifically? Ronnie, go ahead.
Two
How many? How many electrons are they sharing? 2. A covalent bond is a pair of shared electrons, right? We don't ever share just one electron. We share 2 electrons, right? That one brings one brings the other one. I will tell you, beyond the scope of this class, but there are instances where one atom can actually provide both electrons that are shared between 2 atoms instead of one bringing one and one bringing the other. That does happen sometimes, but that's higher level stuff. Like we're not going to worry about that here. Okay. So a covalent bond is a pair of shared electrons. A lot of times we represent that how in a picture. How do we represent 2 atoms sharing a pair of electrons in a picture?
Drawing them like putting those 2 valence electrons in the circle.
We said that's kind of how we described it, but usually to shorthand, how do we do it? We put a line between them, right?
Oh.
That line represents the pair of shared electrons in the structural formula. So if we see 2 atoms that are connected with a line, that means they're sharing a pair of electrons. Okay? Good there.
Yeah.
All right. Okay, good.
Like if that were to show up on a test, would it matter if you like the dots?
If I say what kind of bond will these form, no, but we'll wait till the end because there is something I want to explain first where it might make a difference. So, not the end, just a little bit later on. All right. Did we fill out any of the back side of the paper today? Okay. So let's start with molecule. Okay. Molecules are a electronically neutral group of atoms held together by one or more covalent bonds. So when we have atoms that are held together by covalent bonds, we refer to that as a molecule. All the atoms in a molecule will have 8 valence electrons, either from the ones that they had on their own or ones that they're sharing with other atoms, right? But that's what we call a molecule.
Don't you learn a lot about molecules in chemistry?
Yeah, I mean that's where we're getting there. You know, this is introducing. You know, this is like vocab words.
Is that class chemistry?
That's chemistry.
I saw it.
All right, good here.
I know.
You don't have to draw these, but here are some pictures of some molecules. What do we notice about the atoms or the elements that are in molecules? What kind of elements are in molecules? Non-metals, right? Why? Because what is a molecule held together by? Covalent bonds, right? And we said covalent bonds only happen between 2 nonmetals, right? So all of these molecules are held together by covalent bonds, and that means that they have nonmetals in them, okay? Good there? All right. Yesterday, and you guys have a picture of this. I'm just going to draw it again to remember where we were. All right, let's go here. Let's go here. Okay. Yesterday, I believe, come on, pen. All right. Yesterday, I drew you this chlorine with its 7 valence electrons, and I drew you this chlorine with its 7 valence electrons, and then we did this, and we said that's a covalent bond, right? A pair of shared electrons between 2 nonmetals, okay? Is this a molecule?
Yes.
Yes. It's a group of atoms held together by a covalent bond. But this is a specific type of molecule because what's true about the 2 atoms that are being held together? They're the same element, right? This is a specific type of molecule that we call a diatomic molecule.
Because there's 2.
Well, 2 atoms, right? Okay. But specifically, those 2 atoms are the same kind of atoms or the same elements. So a molecule that consists of 2 of the same kind of atoms, right? Or 2 atoms of the same element. So we find out that there are certain elements on the periodic table that will form diatomic molecules, but some that won't. Okay? So we know that one element that forms a diatomic molecule is what? I just drew it up on the board. Chlorine. All right. So let's put our thinking caps on. Right. If you had to make a guess as far as one other element that might form a diatomic molecule, what might your guess be? Talk to the person next to you. Talk to the person next to you. 10 seconds. What other element might form a diatomic molecule?
Isn't it?
I know the answer to
All right. So
Alright.
before I started you on your 10 seconds, one of the suggestions was fluorine, and that's true. Iodine might be another one. Fluorine, iodine, bromine.
Carbon.
All right. So now we find out though that it's not all the elements in that family. Okay. So we find out that there are 7 elements on the periodic table that form diatomic molecules. Right? Fluorine, chlorine, bromine, and iodine. Okay. So those 4, they're all in the same family. That makes sense. Okay.
Is it because they all have 7?
Yep. They all have 7 valence electrons. So, Pat, if we go back to like this picture,
Yes.
right?
Yes, so they can share that.
If we change Cl to F, would this picture look any different? Looks exactly the same. Okay. Next, so we got fluorine, chlorine, bromine, and iodine. Okay. You'll see hydrogen is on the list. Okay. If you go to the other side of the paper, okay, your outline. If you flip your outline over to the front side. The pictures down at the bottom that show the ways that we represent covalent bonds. This is diatomic hydrogen. Okay? Hydrogen's a little bit different than those other elements because how many valence electrons does it have? It has 1, but when it shares with another hydrogen, how many valence electrons do those hydrogens end up with? 2. Is that okay?
Yeah.
That's okay for hydrogen because how big is hydrogen? Right?
Very
We said the small
that
elements
big.
are okay with only 2 valence electrons, right? They only have to fill up that 1s level, okay? So fluorine, chlorine, bromine, iodine, hydrogen, okay? And then there's 2 more, right? Did you guys see the two that were on there? Do you want me to put the list back up?
Yeah.
All right. The 2 other ones are nitrogen and oxygen, okay? So do we have those 7 written down? So fluorine, chlorine, bromine, iodine, hydrogen, nitrogen, and oxygen. Even though other elements might fall into the same family as either one or more than one of those are the only 7 that we find out there in nature that actually do this. Okay? So if you look at oxygen, the next one down from oxygen is sulfur. We don't see diatomic sulfur. It just doesn't happen out there in nature. So these 7 do happen. Okay? All right, good with these? Okay, let's draw another picture. All right, so here is oxygen. 1, 2, 3, 4, 5, 6. Because what group is oxygen in on the periodic table?
16.
16.
And
Right?
6 valence electrons.
Yeah, 6 valence electrons.
Good job.
All right. Here's oxygen. 1, 2, 3, 4, 5, 6. Okay. 6 valence electrons. Oxygen is looking to do what?
Gain 2.
Gain 2.
So
Right.
we share 2.
So here's this. Okay, so we shared that, right? But if we look now and we count up oxygen's valence electrons, the one on the left has 1, 2, 3, 4, 5, 6 of its own, plus the one that it's sharing with the other oxygen. Now it has 7. Is it in its lowest energy state yet? Not there. Okay. But hopefully you make the connection here, right? Okay. Okay. They have still sort of a single, they each still have a single electron there that they could share, right? Now if we count up oxygen's electrons, right? 1, 2, 3, 4, 5, 6 on its own, 7 that it's sharing there, 8 that it's sharing there. Now is it in its low energy state?
Yeah.
Yes, it is, right? So we could represent this molecule like this. Okay? Good there?
So if an element had like 5 valence electrons, could they like share 3 each?
So, next on the list, the other diatomic molecule that was on the list was
Sodium. Oh wait, no.
nitrogen. Find nitrogen on the periodic table.
Group 15.
Group 15, right? Group 15 means it has 5 valence electrons, right? Right, Devlin? Just like you were saying. Okay. Here's another nitrogen. 1, 2, 3, 4, 5 valence electrons. Okay? Share here, share here, share here.
Wait.
Okay? So if we're going to draw a structural formula, now it's going to look like this.
So pretty much whenever you draw a structure or something
Wait,
that's
why can't?
Let him finish his question.
so it would be like chlorine would be Cl but with 6 valence electrons is equal to Cl with 6 valence electrons.
Not equal to, right?
Oh yeah,
It's a line.
a dash.
Okay.
Also, you have to fill out the
Okay. So there's chlorine structural formula,
It's only 6.
Right. right? It's got 6, but we said each line represents what?
Shared valence electrons.
How many shared valence electrons? 2 shared valence electrons. So the chlorine has 6 valence electrons of its own, plus the line, that counts for 2, that's 8, right? Here, oxygen has 4 valence electrons on its own, plus these 2 lines. Each of those lines represents how many electrons? Each of those lines represents how many electrons? Each line represents 2 electrons. So if you count the 4 that oxygen has by itself, plus the 2 lines, which is actually 4 electrons that it's sharing, that gets it up to 8. Okay? Rachel, go ahead.
When you draw the structural diagram, you have to have the dots too.
Usually we show the dots because those are electrons that aren't being shared, right? Rachel, the structural formula a lot of times is a to help you out sort of thing. As you go on more and more and more, sometimes we won't draw those, like, you know, that, like, sometimes as you get more advanced, as you get more knowledgeable, you know, O double line O, you realize that oxygen still has valence electrons there. It needs to have 8. But for starters, I'm drawing them there to show you that, yeah, they have 8. Some are being shared, some are not. Okay? So, Ken, back to your question from before. If I gave you and said draw the bond between oxygen and oxygen, right? You could do this, that would be fine, okay? But I also might give you a question on the test, like how many electron are these 2 oxygens sharing? You need to know that each line represents 2 electrons, and that means 4. Okay? All right. Question. This is a tough question, too. Pay attention, because, man, this is going to require some thought, right? So, any guesses as what we might call those 2 lines connecting oxygen together?
Double bond.
A double bond. Whoa.
Oh my.
Right?
So
Any guesses? What might we call that one? Triple bond. All right. So, some elements on the periodic table have the ability to form multiple bonds. Some atoms are held together by sharing more than 1 pair of electrons. Okay? This is the last thing on the backside. This is the last section on the backside of your outline. Okay. Some atoms are held together by sharing more than 1 pair of electrons. If atoms are held together by sharing 2 pairs of electrons, we call that a double bond, right? Which results in them sharing 4 pairs of electrons. Or if 2 atoms share 3 pairs of electrons, we call that a triple bond. Triple bond consists of 6 total electrons. Because remember, each bond is a pair of electrons. Go ahead.
Can hydrogen form a diatomic molecule if it only has one valence electron?
Because remember,
Oh wait, no, because are they both losing?
neither one of them is really losing or gaining. They're sharing, right? Because each one of those hydrogen atoms wants to get to how many? Hydrogen is small. It only has to get to how many? Two. Remember? Because remember, when we go 1s, then we go straight to 2s, right? There's no 1p. So the first orbital, the first shell, is full with only 2 electrons. So that's why hydrogen can form that diatomic molecule, even though it only has 1 valence electron on its own. It shares with another hydrogen, and now they each have 2. And that's good. Okay. All right, so before we move on, right?
Would that be the same? Wait, never mind.
Yeah.
Because I was gonna say, would that be the same with the other ones with 1 valence electron?
Yeah, they don't do that. That's why hydrogen. That's a good question, Devlin. Because hey, that's a good question because hydrogen on the periodic table shows up in group 1, but none of the other group 1 elements do that because hydrogen, even though it has 1 valence electron, isn't a metal like the rest of them. It's more non-metal, and that's why it gains instead of loses. Right. So even though hydrogen is in that group 1 column, none of the other ones in that group 1 column form diatomic molecules. Okay. All right. So one question logically follows from these drawings that I have up on the board. Right. One question logically follows here. Right. What's the question that somebody wants to ask about these double bonds and triple bonds? It's not the question I was thinking of, but I don't quite understand the question, so let's just disregard. So, okay. Ronnie, what element might be possible for us to do 4 shared pairs of electrons?
It's a metal. Carbon.
Do you understand why, or did you just say it because Devil said it? That's fine. It's fine. You can just say it. You know what I'm saying. It is carbon, by the way. That's the right one. So here's carbon, right? 1, 2, 3, 4. Here's carbon. 1, 2, 3, 4. 1, 2, 3, 4. Okay. So, is everybody happy here? Yeah, everybody's happy here, right? Everybody's got 8. Okay. But we run into a problem. When we look at these elements, oxygen and nitrogen, they're sharing, in this case, 4 electrons, and in this case, 8 electrons, right? Sorry, not 8, 6, my bad. But as they share those electrons, right, the electron density is very strong in this area, right between those 2 atoms. If we looked at like the dark sections, light sections around the atoms, around the nuclei, it would be real dark in between these 2 oxygens because there's lots of electrons there because they're sharing them. It would be even darker around nitrogen because there's even more electrons that they're sharing. But the more and more electrons that they share in between that space, what do we know all electrons do to each other, though? They repel each other, right? So while on a piece of paper, we can draw this, right? We find that this never happens in nature. We don't ever find quadruple bonds. Why? There's too many electrons there. They don't stay in that space enough for them, carbon and carbon, to share them. And so we don't, while it fits all of the criteria for a bond, 8 valence electrons, non-metals, we're sharing, we never see that in nature. Pat, go ahead.
Oh, so you can only have single, double, and triple.
Single, double, triple. Yep. We don't ever see quadruple. And we can't get past quadruple because then how many electrons are we talking about? Let's say if there's like a quintuple bond.
Yeah,
5.
10.
Yeah, it's 10. And
You can't have 10.
right. No atom wants 10 and wants 8, right? Maddie, question, go ahead.
So like the examples that you gave us of nitrogen,
Yep.
are those the only ones that work?
Those 7 those 7 that were there and underneath diatomic molecules, those are the only molecules that we find that will bond with another atom of the same element. Yeah, just those 7. Even though on paper we could see how other elements might work, we don't find it out there in the real world. Okay, yeah, just those 7. All right, good there? All right, pull out the outline that I gave you today. First off, I apologize for this being 2 pages stapled together. I had meant it to be front and back, and I don't know why it came back that way. So the back of both those pages is blank. I apologize. All right, but anyway, that outline deals with writing chemical formulas and naming covalent compounds. But if you look at the calendar for today, so if we go here. On the calendar, it says naming molecular compounds. What is a molecular compound? Oh, good.
Well, a molecule, isn't that when there's 2 like of the same non-metal?
That's a specific molecule called a diatomic molecule.
Right.
But any molecule, we said, go back to your outline that we were just working on. What's our definition of a molecule?
A molecule is a electron.
Right, so if it's just 2 different non-metals, not
So
the same.
a molecule is any atom held together by covalent bonds.
H2O.
And that means we're dealing with nonmetals. Okay?
H2O2.
So at the top of your outline where it says formulas and names for covalent compounds, we could also substitute in the word molecular into that, right, for covalent. Covalent and molecular basically mean the same thing because molecules are covalent bonds. So you might want to write that there. If you see covalent or if you see molecular, that's basically the same thing. Okay. All right, good there? So let's first talk about formulas. What does a formula tell us? 2 things a formula tells us. All right, go ahead. How many of an atom there are and what the atoms are, what the elements are, right? A chemical formula is a shorthand way of describing the atoms that make up a molecule or a compound. A chemical formula is a shorthand way of describing atoms that make up a molecule or a compound. And like Pat said, formulas tell us 2 things, right? They will tell us what types of atoms, okay, and we use the chemical symbols to represent that. And then it also tells us how many, or the ratio of those types of atoms that we need to get everybody to 8 and make everybody happy. All right, good there? Okay, so names then. Naming covalent compounds, we said we could also substitute in the word molecular there, so we could also say naming molecular compounds. Okay. Just like ionic compounds, molecular compounds, the name is based on the names of the 2 elements. And we say the most metallic element, metallic in quotation marks, is written first. If we're comparing nonmetals, which nonmetal is going to be more metallic? Ones that are located kind of where?
Like
Closer to the left, right? Because that's where metals are in the periodic table. So generally speaking, the element that comes farther to the left is written first. Okay? If both of those elements are in the same family, the lower element is written first. Okay, good.
So say it's like fluorine and chlorine.
Yep.
So you just be like fluorine, chloride.
Lower element is written first. So
I think you meant atomic
Yeah.
numbers.
no, sorry, lower actually in the family. So yeah,
I
we
think you
we
meant
could say
atomic.
higher atomic number is written first. You could say that too. All right, good there. With those, okay. But there's something that's a little bit different, and here's the reason why. let me draw you a molecular compound. Okay? Ready? Here, come on. Maybe not. Oh, I turned it off for some reason. All right, so here is a structural formula for a molecular compound. Okay. First, anybody know what that compound is? Anybody?
Hydrogen chloride. Dye.
It actually has a common name that it goes by. This is methane. Okay. Anybody hear of methane before? Commonly referred to as swamp gas.
You can die from it.
Yeah, you can die from it, yes. So it's also very flammable too. Okay? All right, so here's the structural formula for methane. And here's the chemical formula for methane. Okay? I know it seems weird because I just told you that the ones written to the left come first, and hydrogen seems like it goes to the left, but really when we're talking about it as a non-metal, it's way over in group 17 because it's looking for one valence electron. Beside the point. Okay? All right, here's another structural formula. Okay.
That's triple methane.
Okay. So, what's the ratio of carbon to hydrogen in methane? In methane.
Just steal people.
1 to 4. 1 to 4.
That's
Okay. So, is the ratio in the picture on the right 1 to 4?
No.
It's not. Right? So, here, this formula is this, C3H8. Okay? Anybody ever hear of propane before?
Propane gas.
Propane gas, yep. That's it on the right. All right, so we have different formulas because the ratio of carbon to hydrogen is different in these two elements, or in these two compounds. But if we look at names, it says the name is based off of the two elements, and the most metallic one comes first, et cetera, et cetera. What's true about the two elements that are in these two compounds? Well, which two elements are in both of these compounds? Carbon and hydrogen, right? So if the name is based off of the elements that are there, we have a problem because these both have the same elements, it's just the ratio is different, okay? So here's how we handle that in molecular compounds. We use a system of prefixes to indicate the number of the atoms that are in that compound. Okay? So we use prefixes to indicate the number of atoms in that compound. Okay? And the prefixes, okay, look like this table right here. Okay? Prefixes, one word.
Oh, I thought you.
All right, so I think looking at this table, most of these you're pretty familiar with, right? You know that mono is 1 and di is 2, and you've heard of an octopus before, and you know that kind of stuff, right? Okay? So I think you're probably familiar with these things, okay? But there are some rules that come along with it, all right? So down at the bottom of the page, there are a couple of practice problems. These practice problems right here. Here's what I'm going to do. I am going to grab these, okay, put them in a new page, and let's do a couple of them together. I'm not going to do them in order because there's a couple of things that we have to talk about. Okay? All right. So first one I want to talk about is the very, very one at the bottom, N2O4. Okay? I'll use red for that. All right. So first, the name has to represent the ratio, and we use the prefixes to represent that. Okay, so how many nitrogens are in that formula? 2. Prefix that represents 2 is what?
Die.
Di. So the first word in the name of this compound is dinitrogen. Okay? All right. Second element that's in this compound is what? Oxygen.
But there's
Right?
four.
Okay. But there's 4 of them. So, a couple of things here, right? 3 things we have to talk about. Okay? 3 things for the second word of this compound. 1, the prefix is tetra. Okay? So we'll start with tetra. Okay? Okay? Then the name of the element, right? Oxygen, but because it's the second word, we change the ending. So tetraoxide.
Is that for everyone?
Now, yeah, you always change the second word to the IDE ending. Okay? Now, one last thing. Okay? And if you don't get this exactly right on the quiz, like if you wrote dinitrogen tetraoxide on the quiz, you get credit for that because you did what you were supposed to. But just from a wording standpoint, a pronunciation standpoint, tetraoxide has 2 vowels next to each other, right? They got an A and an O. Okay? Generally, when that's the case, we will drop the vowel on the prefix, and the actual name of this compound is dinitrogen tetroxide. But like I said, if you wrote tetraoxide on the quiz, I'm giving you credit for that. That's fine. Okay? All right. Good there? Okay? Next, let's take a look at this one right here. Okay? H2O. I know you guys know that that's all has a name, right? It has a common name. We call it water. But we can use the naming system that goes along with it. So, what's the first word of the name of this compound going to be? Dihydrogen. Okay? Okay? And then we have how many oxygens here? Just one, right? So we use mono, right? And then oxid, and we change the ending to IDE, so dihydrogen monoxide. Okay? Or if you were pronouncing it phonetically, it would be monoxide. Right? 2 O's, right? That's funny. That doesn't sound right. Okay, so again, vowel, right? We get rid of that 1 O, and then it's just dihydrogen monoxide. Okay? Good there? Okay. One last example that I want to do for you is this one up here. Okay? CO2. I'm assuming most of you know that the name of that compound is what?
Carbon dioxide.
Carbon dioxide. And that is the proper name of this compound. Okay? I think the dioxide part is probably okay. Okay? I realize that that goes against something that I just told you because there's 2 vowels together and I didn't drop the I on di. Okay? Again, if you...
It's just the oxide?
No. In this one, we keep it. Right? So it is dioxide. Yeah, so it's like, there's situations that go there. However, something maybe a little more important, right, is what? Where's the mono? Right? If the first element in the compound only has 1, we don't use the mono. Okay? So you use the mono if the second element has 1, but not if the first one has 1. Just like this one right here. Okay? So this one right here, CO. You don't use mono in front of carbon here because it's the first one, it's the first element in that formula, but then you would use the mono prefix for the second. So that's carbon monoxide. Okay? So, rules, right? Prefixes. Unless the first element in the formula only has 1, then you drop the mono. Second, you change the ending of the second word to IDE. Third, if you have 2 vowels together, sometimes we drop that vowel, right? Okay? Mono, tetra, penta, that kind of stuff. Good, Jafar.
What do you do with the second one?
Well, you tell me.
'Cause I don't know what you would call the second one.
Let's do it together. Okay.
Yeah, what would you
Carbon
call the second one?
tetrachloride.
There we go. That's exactly what you call it. So carbon, because all right. So here, let me get another color. All right. So first word here is going to be carbon. Okay. Jafar, again, we don't use the mono because that's the first element in the word. Okay. The prefix for 4 is what? Tetra. Okay. But then, because that's not it, because chlorine doesn't start with a vowel, right? So tetra, and then chloride, because we changed the ending of the last word. Yep. All right. So on the and that packet that I gave you today, the 2 pages that are stapled together, the second page is just a bunch of practices, names and formulas, right? That's your homework for tonight. Answers, I believe, are posted on the calendar. I will check right after you guys leave. If they're not posted, I will post them for you. Okay? Tomorrow, we get into polyatomic ions. Woo!